looks fine. One, two, three. One, two, three. 1, 2, 3. Checking. Check, check, check. 1, 2, 3, check, check, check. 1, 2, 3. Begin.
Um, Hello and welcome to this Java meetup at CRX. My name is Thomas Brusa. I'm heading product and IT here. Today my role is to welcome you, which I just did now, to make sure everybody is aware of food and drinks and doesn't hold back. And then to leave the stage to Sergey. He's going to talk about unpolished Java gems, so have fun. And happy to talk to you also in the aftermath of the talk.
Sure.
Thanks.
Thank you.
Okay. So yeah, I'm Sergey. I'm a developer here at CRX. I'm glad that you all came here today. I hope that this talk will be interesting for you. Mostly I will do the talking, but you can interrupt me at any time and ask questions because we're such a small group. So if you have any questions, just go ahead and interrupt me. So why did I call my talk Unpolished Java Gems? Because I would like to talk about some interesting features of Java gems, which are, to me, or at least to my mind, are a little bit rough on the edges. So I will talk not only on these features, but about how are they compared to the same features in different languages based on Java, in Kotlin and Scala. And also, how could all this evolve in the future in Java, I don't know, 11, 12, or in any given number. So the first feature that I'd like to touch is the generics. It's probably one of my favorite features because it was a big deal when it came out, and it's still evolving in Java, and it is pretty easy to use it incorrectly or not as planned. So a little bit of history first. Generics, well, actually generics is a concept from generic programming which appeared first in ML in 1973. So basically that means that you write code that doesn't depend on particular objects, just some generic code that you can substitute any kind of objects or values for that matter. So the first guys who implemented generics on Java were these two guys, Phil Wadler and Martin Odersky. These are pretty well known in programmer community. Phil Wadler is one of the developers of Haskell, so he's a pretty cool functional guy, and Martin Odersky is the developer of Scala. So they developed generic compiler for Java, which already could work with generics as early as 1998. But we know that generics appeared in Java only in 2005. So what happened? 2004. What happened? So actually, in 1998, Java 1.2 came out, and there was a huge collection overall. Collection library. So the developers from Sun decided that, well, that's a pretty cool feature, but we will have to make another overhaul of collection API in the next release, so why would anyone want that? Let's keep it away for a while. And then, in 2004, some developers took these, the work of these guys and implemented it inside the Java 5 as we know it. And mostly the generics did not actually change from that time much. And this was, so Java 5 was released September 30, 2004. And this, I mean, the generics were a pretty big deal back then, because if you look at this Teriobi programming index for September 2004, the only language here in the top 10 that had something like generics was C++. It was the templates. Well, the templates actually, it's a pretty interesting topic because back then there were many interview questions on what the difference between C++ generics and Java, C++ templates and Java generics. It was an interesting question on the interviews, but I think they don't ask it anymore because back then, many people switched from C++ to Java. Now, maybe not so much. So back then, they had to know it. But still, at that time, this was a pretty innovative feature, generics, in a mainstream programming language. Because if you look at the more modern TIOB index, for example, this is for November 2017, you will see that, well, at least 5 of these languages have generics. Java, C++ as templates, Python has type annotations with generics also, C# has generics, well, JavaScript. Visual Basic has generics because it's based on the .NET platform. PHP, no. Well, Delphi also has generics. Well, for some reason, assembly doesn't have generics. I don't know why. But this is a common mainstream feature nowadays. So for that time, for 2004, it was really innovative. So the first thing I'd like to talk about is a pretty easy trick that probably everyone who wrote on Java for, I don't know, half a year at least knows this problem with generics. That if you, for example, have this list of integers, you created it just like that, and you try to cast it to a list of numbers, you cannot do that. Although it's first when you encounter it, it seems strange. Why can I? Well, the array of integers is an array of a list of integers is a list of numbers. So why can I cast it? It's pretty easy to see why, because if suppose you have this array of integers and 2 different references to it, list of integers and list of numbers, then you could do something like this. You could add a long using this link, and then get this long using this link. So this would be a type error. You received from the list of integers a long. That would be a type error. So this is a practical explanation why you cannot do that. But what's the theory behind it? Well, let's suppose we have an immutable array. We cannot add anything there, but we have 2 references to this array, but we cannot add anything there. We can only receive integers from there. In Java, this is all the same. Well, you still cannot cast it to a list of numbers, although this problem seems to be solved. You cannot change it, so you cannot receive a type error. So why can't you just cast it? Well, because Java doesn't know that it's immutable. If you look at the collection interface, you will see a lot of methods that mutate its state. This is the basic interface of all collections in Java, well, except for map. But map is also mutable. So Java has no way of knowing that your particular instance of a collection is immutable. If you look at the implementation of an abstract of an immutable list in Java, this can be created using the collections.immutable list. You will see that all these methods, they actually exist there, but they just throw an unsupported operation exception. So again, for Java, there's no way of knowing that this list is immutable, in fact. But still, we see that this should be an inherent property of read-only collections. So if your type argument, according to polymorphism, can be cast like this, integer to number to object, then the true immutable list, if it would exist in Java, should be cast like this in the same direction. And this is called covariance in the type theory. So the arrows are going the same way. But unfortunately, you cannot do this in Java, because Java has no way of knowing that this particular list is covariant. You just cannot specify it. We can look at another example, write-only generics. So what's a write-only generic? For example, a consumer from Java 8. It's a write-only generic. You cannot get anything from this consumer. You can only write something inside. Like you write, consume an integer and print it out in the console. Okay, but we cannot cast it to a consumer of numbers. But why? Since this consumer of objects can accept any kind of object and it can accept a number. So why can't we cast it to a consumer of numbers? So we could also look at it that way. So we have a consumer of numbers which can consume number, long, integer, anything. And we have consumer of objects which also can consume these guys, but it also can consume objects. So why can't we substitute instead of this guy, this guy? Well, because Java again doesn't know that this is a write-only generic. still, this is an inherent property of write-only generics. So if your type casts like this polymorphically, then the generic type is cast the other way. And this is called countervariance. And again, you cannot specify it in Java for the types. Well, let's look at the Kotlin, new cool language, which arguably fixes a lot of problems with Java. In Kotlin, the basic collection interface is immutable. You cannot mutate it. Well, if you worked with streams in Java, then you know how to work with immutable collection. Streams are also basically immutable. So no problem with that. You just create a new instance of a collection if you need to change something. But this interface, although it looks very much like Java, it has this interesting thing here, like out E. So this out parameter basically means that you only get something out of it. You cannot write inside anything. And in Kotlin, you can easily cast this list of integers to a list of numbers, no problem, because Kotlin knows that this particular type is covariant. The same in Scala, although it looks a little bit different, a little bit less like Java, but still, well, trade is sort of like an interface with partial implementation in Scala, and this square brackets, basically this is a parameterized type. So this little plus here means that this is a covariant collection. So you also can cast a sequence of ints to a sequence of any objects. Any is a root object in the hierarchy of Scala. Also no problem here, because Scala knows that this is a covariant type. What about multiple type parameters? Well, there is an interesting type that we all know and love in Java that has two type parameters. One of them goes inside, the other goes outside. So this is, of course, the function, the interface function. And since this one goes in and this one goes out, probably they should be countervariant and covariant correspondingly. Well, if you look at the function in Kotlin, you will see this in and out that we already see. So in Kotlin, the language knows that the function is inherently countervariant by its first parameter and covariant by the second. Okay, Scala, same thing. Well, only here, minus and plus. And that's actually a very interesting difference between Kotlin and Scala in the general idea of their syntax. Because in Kotlin, they took this approach from C#. They also call it in and out. Because this goes in, this goes out. This is pretty easy to understand by not going too deep into type theory. In Scala, they decided to call it minus and plus because this is counter variance and this is covariance, the direction of the cast. But is it really so bad in Java? Well, actually, no. In Java, there is a very interesting thing that's called use-site variance. And now, an interesting question that often comes up on the job interviews. What can we add to the list that is described like this? What can we add inside it? Does anybody have any opinions on that? So what objects can we put here? Like number, long, integer, objects.
Any subtype of number.
Any subtype of number. Okay, that's, well, it looks like it should be that way, right? But actually, then what's the difference between this and this? Here we also can add any subtype of number without any casting because integer is number, so we should be able to add it here. So what's the difference between these two notations? Actually, the first notation means that this reference is a reference to any kind of a collection which type parameter extends number. So this could be a reference to an integer, we don't know that. This could be a reference to a list of numbers. or to a list of longs. We don't know which exactly. So what can we say about this collection? What can we add to any of these collections? Nothing. Only null, because only null can be cast both to integer and to number and to long. Nothing else. So using this reference, we cannot actually add anything. The correct answer is null. But why do we need this reference? Because of what we can get out of this reference. Because since this is a reference to a collection that is parameterized by integer or number or long, and anything that we get out is a number. So the same thing is about this notation. Question mark super number. What can we add to it? Well, this means that this is a reference to either a list of numbers or a list of objects. So what can we add? Numbers, because numbers extend both this and this one. So we can add anything that extends number. But what we can receive out of it, well, anything, object. Because from here we can accept anything. So this is basically the use site variance that we have in Java. We cannot say that this collection is covariant or countervariant, but we can say that this reference to a collection is covariant or countervariant. It looks the same thing, but not exactly. So a little digression. In Scala, there is a type hierarchy that has so-called top types and bottom types. You don't hear about it much in Java, but in Scala this is a big thing. So top types, sorry, top types is the types that anything that are the super type of everything else. The bottom type is something that can be cast to everything else. So null can be cast to any other object, as in Java. So this is basically the bottom type. And any, which is the root of the hierarchy, corresponds to object in Java. It's something that any other type can be cast to. So in Java, you don't have type null. In Java, you have only the instance of this type, this value null. And this is the problem with the Java type system. Because if you go back to this interesting picture where we can only add a null to this collection, this is basically the covariant, the covariant collection. So it should be immutable. You shouldn't add nulls to it, because this actually doesn't make any sense. Why would you want a collection to which you can add a null? I can't imagine a use case for this actually. So this here is a hole in the type system of Java, because bottom type or null is something that should not have any instance in the language. But in Java it has an instance, null. If you wouldn't have an instance of null in the language, then you could easily say that this collection is immutable because it is covariant. Okay, that's about top types and bottom types. Well, how do we benefit from variance? Well, if you remember, for example, this map function from Java 8 that any stream has, this map function, so it applies some function to every element of a stream and returns a new stream with the results of this function. So if you look at it, you will see that here we see this same super and extends keywords that basically state that this goes in, this goes out. But this is only on the use side. You cannot say the same for the instance of a collection, that this is covariant or countervariant. Here, this is the use side. But if you look at the same function map in Kotlin, for example, you won't see any out or in here, because in Kotlin, any function of one argument is inherently countervariant by its first type parameter and covariant by its second. You don't have to specify it in every use site, because this follows from the definition of the function in Kotlin. And the same in Scala. you don't have to explicitly specify that this is in and this is out. Will we see something like this in Java anytime soon? Well, there is a JEP, or so-called Java Enhancement Proposal. This is a sort of like GSR, but for the developers of JDK. This is called Augment Use Site Variance with Declaration Site Defaults. So this basically means that we could describe the collection with these in and out params, and we won't have to specify it in every place where we use this collection. And that would be pretty cool. But there's not even an assigned version of JDK yet, so we don't know when it's coming, even if it's coming. There's an interesting related JEP, 218, which, oh, sorry, no. First, in this JEP about covariant and countervariant annotation, there's a Strawman syntax for Java. How could it look like in Java? Well, this is Java. There are a lot of letters in Java, so let's call it countervariant and covariant. Well, you already write a lot of letters, so it won't make any difference. But still, yeah, after completion. So it's fine. Well, this is a little bit academic for me. I think they should stick to in and out like in Kotlin, but whatever. The main thing that this feature would appear in a language, that would be great. But this requires class file changes. So this requires that you describe these features in the bytecode. So this wouldn't be backwards compatible probably. There's an interesting JEP which is called Generics over Primitive Types. And I actually expected that it would be released in Java 10, but looks like no. So what does it mean? It means that we can write something like this. We can use primitive types as type parameters in generic. That would be also really cool, especially if it would be optimized somewhere inside, so that we don't keep the actual list of wrapped integer objects, but we keep an array of simple integers. That would be a pretty cool optimization. But still, also no release date, no nothing. But generics don't stop there, because there's an interesting feature that's called Reified Generics. But before I go into that, I'd like to tell you a little story with a moral. Once I got interested in a language which is called Elm, sort of like Nightmare on Elm Street. Elm. It's a language that is based on JavaScript. It transpiles to JavaScript. You know, there are lots of such languages floating around in the recent days. So the feature of this language was that it's very, very functional and very rigid. It has this very strong type system. So one of the selling points, if you go to its website, they say, well, you will never again see in the browser console this dreadful message undefined is not a function, which all JavaScript programmers know and hate. And I decided to try out this language. I cloned the repository. I built several examples. I ran them in the browser, and the first thing I saw in the console when I ran them was undefined is not a function. So this, why am I talking about Reified Generics here? Because if the platform on which you build the language has some limitations, they will find their way through. You will encounter them. So you can build Scala or Kotlin atop of Java, but they still have the same issues as Java. For example, you cannot have real Reified Generics in Scala or Kotlin. So what's Reified Generics? Reified means materialized. So these generics are present during runtime. You know the type of a particular collection, for example, at runtime. This means that, for example, you can have a parameterized type, like a wrapper of something of some type, and then just create a new instance of this type parameter. This is possible in C#, for example, but not in Java. not in Kotlin and not in Scala. But in Kotlin, there's an interesting feature. It allows you to, in limited places, use this reified keyword. This is an inline function. You can say that this parameter is actually reified, and inside this function, you can use this pretty horrible syntax. If you guys know Kotlin, you know that this is dereferencing of a potentially null value. So you say that, okay, I'm sure that there is a primary constructor there, and I want to call it. I'm really sure that it's there, and I call it. If it's not there, well, it will be a runtime error. So that's not really helps us with type safety. But still, at least something, Kotlin has some reified generics.
Smells like reflection.
Smells like reflection, true.
Which you
Yeah,
do
yeah.
it in Java. More or less the same, obviously.
Yeah, right.
I'm sorry?
So, well, that's probably all for generics. I really hope that this part of the language will evolve. Probably sometime in the future we will see something like that. But Java always went its own way and evaded different complex topics by its own decisions and solutions. So another topic I would like to talk about today is the functionalness of Java. Can Java be considered a functional language after what we had in Java 8, for example? Well, for me, functional language is a language where the functions are first-class objects. But what does that mean? First of all, we can assign functions to variables. We can pass functions as arguments, and we can return them from other functions. This means that we can work with functions as with any other objects. Can we do this in Java? Well, as a matter of fact, yes, we can do this. In Java, everything is possible with functional interfaces. But there's a catch. A functional interface is an interface with a single abstract method. And you can instantiate the instance, create an instance of this interface by using this literal. Well, it looks pretty easy, and it looks like a lambda. But the problem here is that you can create another functional interface. Well, actually, we have in Java already a functional interface with one argument and return value, which is called a function. And you can instantiate the same functional literal, instantiate it with the same functional literal. So these things are pretty common. You would expect that they are the same, but they are not the same, because you cannot cast one to another, because these are different functional interfaces. So this seems pretty strange to me, because in functional programming, a lambda just is defined by its parameters and return value. So in Java, lambda has something else. It has a functional interface. And actually, I heard an opinion, well, that's a feature of Java. You can segregate different interfaces, different lambdas by different interfaces. You can say, okay, here I require this interface, and in this place I require this interface, and I don't want to mix and match them. So this is a feature. Well, I don't agree that this is a feature, because for me, the language should provide ability to make more abstractions, not restrain me to less abstractions. This basically means that I cannot create a single abstraction of what a function is. I cannot create a library, a functional library that takes functions and do something with them without restraining it to a certain interface, functional interface. The same problem is with consumers. So, for example, I have this class with a couple of methods, and I can reference a method by this syntax, with double colon. This is a function that takes integer and returns an integer. It's pretty easy. So we see a method that takes integer and returns an integer, and we can refer to it as a function. Cool. But we have another method that doesn't return anything, just void. So this method cannot be cast to a function, because void in Java is not actually a type that has an instance of void. Void is not an instance, it's just a keyword. So this doesn't match. So to create a reference to this method, you use another class, which is called the consumer. And do these two classes, function and consumer, correlate in any way? Can I abstract over them? No. These are two completely different interfaces. So again, there is no single abstraction for the functions. And I cannot write a generic code that works with any kind of function, whatever it returns. Well, this is a design choice of Java from the early stages, that we don't have value that is returned from the functions that return nothing. We just have a keyword that means the function doesn't return anything.
Can I assign a process to a consumer and ignore return value?
No. No. So this you only can assign a method that doesn't return anything, that is void, to a consumer. So, well, how does it look in Kotlin? Well, in Kotlin there's no functional interfaces, they're just lambdas. So you have this fun, which is instantiated with a lambda, and you can cast it to any other val, which is a value, that has this type, integer to integer. So it takes integer and returns integer. And you can cast any kind of method or function to this value, no problem. The same is regarding to the functions that return nothing, because function that return nothing is basically a function that returns unit. This is a type that doesn't have any instances. It just signifies that its function returns nothing. But it's still a type in the type system. So you can create a value which is typed by integer to unit and cast a method to it without any problem. So this is a single abstraction. The same in Scala, except the functions in Scala are called def, so no fun in Scala. But still, it looks pretty much the same. You don't have to specify a particular interface, so there's nothing that could go wrong. And you can create a functional library that operates on any kind of a function. Another interesting topic is closures. So regarding the functionality of Java, closures. Well, there are closures in Java, definitely. Can we say that lambdas are closures? Yes, because they can access some external values. Like this lambda, for example, multiplies its argument by this multiplier that is external to it. But we cannot do this thing. If we change the multiplier, the compiler will fail at once. It says that this is not a final variable. We should not specify this final, but the compiler watches that we don't change it. So it has to be effectively final. Can we call such a lambda a closure? Well, technically, yes, this is a closure because it accesses some external state, external variables. But I like to call it a closure with an asterisk, a big asterisk, because for me, a closure is this kind of thing, like in Scala. You can mutate this variable. So this thing actually captures not the value of this variable, but the reference to this variable in Scala. So you can change it however you want. And the same, of course, in Kotlin. Looks pretty much the same. So is Java a functional language yet? I think that this is really great, and that in Java, in the recent years, some really cool functional features appeared. But for me, I cannot call this language functional until I can abstract over all functions. So there's no unified function hierarchy. There are special cases for consumers and suppliers. So suppliers basically are functions that don't take any kind of a parameter. And there are special cases for primitives. You remember that in streams you have this map method, but you have also map to int, map to long, and so on. So there are special cases for primitive values. And no real closures. So for me, this means that Java is not a functional language yet, but the features that are there are really, really great, and they should be used to their extent. Okay, another thing, another feature or unpolished Java gems that I want to talk about today is the optionals. And I want to talk about them in the context of anti-patterns, so working with optionals. So, what's an optional? Well, we can take any kind of a value and wrap it inside this wrapper, optional. It is parameterized by the type of this value. And then we can do something with this value, whether it's present or not. So we can wrap, for example, a null value. But the problem is that to wrap a null value, we use another method. We use method of nullable. If you try to wrap null value with off, you will receive an exception. So this is pretty strange because optional was invented to fix, or at least to ease the problem of nullability in Java. And here I have to check if the value is null or not null, and then call the corresponding method. So it doesn't help me much. But still, well, this is a rough edge that could be polished. But the first anti-pattern that I wanted to talk about is this one. So if you see this in the code, optional has two interesting methods, isPresent and get. isPresent checks if a value is present. If the value is null, then it returns false. Get returns wrapped value. So what's the problem with this code? It seems legit, but the problem is that it doesn't differ much from this code. So here the same, we check the value for null, and if it's null, we do something. If it's not null, we do something with it. If it's null, we don't do it. So this is longer and more cluttery, and it's not really visible why do we have optionals in the first place if we work with them like this. So the more idiomatic way of working with optionals is, of course, like this. So since optional is a wrapper with a value, then we can map over values inside this wrapper, over one value or zero value. So we can think of it as a collection of 0 or 1 elements. So we can map it, and then if there was nothing, this function wouldn't apply. And we just return 0, for example, or some default value. So this is an idiomatic way of working with option. But still, there are some places where this is present and get pattern would come in handy. For example, if you write some template code, so this is JSF, for example. So actually using isPresent and get in functional languages like Scala is usually considered an anti-pattern itself. So they are there just to be some escape way of using optional in such weird cases where you use it, for example, in a template. Usually you should use it like this with the map. Another interesting case is this one. So I'm not sure if this is an anti-pattern because, well, you want to have an optional field in your class. What's so bad about it? It seems a pretty good use case for an optional, but the problem here is, first of all, that an optional is not serializable. So usually, if this is your domain class, then you persist it to database, you probably save it to the user session, and then it could be passivated or serialized, and then you would get an error. So this class is not serializable because it was not intended to be used that way. If you want to have a field or value inside your class that is optional, you should not substitute the getter, but maybe create a special method for it. For example, I like this convention when you call them maybe address. So it returns optional of nullable address. But the getter for this field is the same old getter that returns a string. So if you want to work with the value as an optional value, you create a separate method for it. And everyone's happy. And you don't have any problems with serializing. Another interesting problem with optionals There's an interesting metric that if you use Sonar or PMD or find bugs, you probably use it. It's called the cyclomatic complexity. This is a metric for a method, usually it's calculated, that means how many different ways of going through this method there are. So basically each if or else or case which or for creates an additional +1 to this cyclomatic complexity, and if it's pretty high, for example, if it's greater than 10, then it looks like this method should be refactored because it's too complex. It's complex to refactor it, to understand what's going on, to test it, and so on. So, for example, you have this very, very complex method, a lot of things is going on there, and your Sonar build is failing because, hey, you have a cyclomatic complexity of 12, for example, and you have to reduce it to at least 10. So you see this part of the code which checks something for null, and if it's not null, we do something with it. If it's null, then we just throw an exception. Well, you look at it and say, what if I rewrite it with an optional? For example, like this. So we say optional of nullable, this variable. Then we say map and do something with this variable. And if there's no value, then we just throw an exception. So Sonar looks at this method and sees, okay, cyclomatic complexity is reduced. Probably we did some good thing here. But actually, if you look at these two parts of code, this is, well, at least to me, definitely easier to read and understand than this one. So this is pretty obvious. This is obscure and complicated, especially if it's not like 2 lines or maybe 10 lines there. It's really strange. So, and actually the cyclomatic complexity didn't go anywhere. We just tricked the Sonar into believing that we reduced it. Because here we have 2 branches of execution. This is branch of execution number 1, and this is number 2. We just tricked the Sonar. So there's really not much sense in refactoring code this way, only if you want to irritate the person who will support it. And what you should actually do with this method is to split it into maybe less complex methods, into several methods. So this is not a way to refactor. Okay. Another interesting problem with optionals is that optionals, can be thought of as collections, but they cannot be streamed, at least in Java 8. So if you look, if we take this class with a field and with a method maybe address which returns an optional of this field, and try to, for example, find or print all addresses of people who have addresses, we will have to write this very cluttery code. So first we take this optional address, then we filter all the values by the optional values that are present, then we get them, and then we print them out. So this is boilerplate. This shouldn't be here because optional is basically a collection. Why do we need this here? Why don't we just stream it or flat map it? And we can do this actually in Java 9. Because in Java 9, optional has the method stream. And we can just say flat map. Flat map means that we stream this value and we return multiple streams and then just flatten them into one stream. So the same is in Scala. But in Scala, we also have these optionals, but you can easily use them as fields of classes. So this is a class person with a single field address. So this is a syntactic sugar to create a class in Scala. So this is a class person with a single field, which is type option. You can do this, and this is encouraged in Scala, no problem. And if you want to make something like I've shown on the previous slide, you just make a flat map from person to address, because optional is the same as a collection in Scala. They are very alike, and they have the same methods. So this is very easy and very understandable what you want to make here. In Kotlin, it's a little bit more complex, because Kotlin doesn't have optionals. It has these nullable types. So this question mark means that this value could be nullable. If you don't have this question mark after the type, then this value doesn't have null, and it is null safe. But there are no options. So since there are no optionals, the same code is a little bit trickier because it requires us to use a special method that was designed particularly for this purpose. Map to not null. So to me it looks a little bit strange because to evade the problem with options, they required to create a new special method for this case. But basically it makes the same as we saw on the previous slide. Okay, and for the last topic today, it would be a very serious topic. It would require a lot of brain power, both from me and from you, I think. So let's start from a very simple example. So suppose you have a task. Business analyst came over and said that, okay, I have the specification, you have to implement it. It's a very simple specification. There are just 3 simple steps. Probably you also know them well. They're very simple. This is the first step. This is the second step. Well, it's not really specified, but you know what to do, right? And this is the third step. So very easy. But the business analyst doesn't understand the complexity of the coding because we have some problems here of which he has no clue. So a business analyst expects that we just write 3 simple methods: collect, monetize, and profit. And that's all. What else there is to it? But there is some inherent complexity that he doesn't know about. For example, these methods have to be implemented as they have to work on the collections. So we have to execute these methods to every element of the collection and then receive the result, and then execute the next method to every element of the collection, receive result, and then execute the last method. So this is a lot more cluttery. But in Java 8 we have streams. So we can write this much easier, like this. So what we did here, we hid the inherent complexity of a collection inside the stream. We still have 3 easy methods which are visible as 3 easy steps, but the complexity of iteration is hidden inside the stream. That's pretty cool. Another kind of complexity is nullability. So for example, these methods could return null. And then we have to check for null. So our code again grows and becomes cluttery and has a lot of null checks. And we again begin to lose this 1, 2, 3 iteration step dynamics. We see a lot of code, but we don't actually know what it's doing, although it's doing a pretty simple thing. But in Java 8 we have optionals, which allows us to implement the same as a 1, 2, 3 step way. So it's a little bit better, a little bit more readable, because we can map different methods to the values of an optional. And if the optional is null, then just these methods won't execute. So this definitely looks better than checking for null all the time. But what we did here is we hidden the complexity inside this optional type. The complexity is that this value can be null. And we received 3 simple steps. Another kind of a complexity, a much more severe complexity, is asynchronous computation. So for example, these methods are complex because they are asynchronous. For example, one of them waits for user input. It blocks and then waits for the input. Another one waits for some condition. For example, for the stocks to rise of the underpants. And the last one does some heavy math, so we have to offload it to some other thread, and we also decided to make it async. So these methods are async, and we cannot call them just 1, 2, 3. we will probably, what can we do in Java? Well, we could use completable future. We could wrap these methods in the completable future. So each of these methods returns a completable future, which in Java are composable. So then you could write something like this. And it looks pretty much the same as with collections, with streams, as with optionals, because we also see that this inherent asynchronous complexity is hidden inside the completable future class. And we just say, well, do thing number 1, do thing number 2, do thing number 3. So it, what it does, it composes these futures and hides the complexity from us. Looks pretty cool and looks pretty similar to what we've already seen before. So there's a common pattern behind these classes. Well, unfortunately, Java doesn't state this pattern, and you barely will see this pattern in books on Java. But functional languages call this pattern. Yeah, let's first. What do these patterns have in common? So, first of all, we have stream, which has methods map and flat map. Optional, which also has methods map and flat map that can be used to compose it. And completable future that has methods, similar methods, then apply and then compose, which are also used for the same purpose, to compose different completable futures and create one big completable future of several. So yeah, this pattern is called monads. I won't describe what a monad is because I would require another hour probably, and you can also read a lot of tutorials on the internet and videos that explain what are those. I like this explanation because a monad is just a monoid in the category of endofunctions. So what's the problem? Of endofunctions, sorry. So this definition is from a category theory book, because monads were first invented as a mathematical object, and then that guy Phil Wadler that I was talking about in the start of my presentation, who was one of the developers of Haskell, he was the first who decided, well, why don't we use them for programming? And, well, I don't want to say that streams or optionals in Java or completable futures are monads. They're definitely not monads because they don't satisfy some laws, mathematical laws, but they are inspired by this pattern, definitely, because you can see this pattern emerging from them. And how is this implemented, for example, in Scala? Well, list, a collection in Scala, has the same methods map and flat map that the stream has in Java. And they do pretty much the same. Option in Scala also has these two methods map and flat map. And future in Scala also has these methods map and flat map that do the same as apply and compose async in Java. So these methods are even named the same way. That this underlines the fact that this is basically the same pattern, although these are completely different objects and they solve completely different problems. But this uniformity in the naming allows to do really, really cool things in Scala that you can't do in Java or even in Kotlin. So I just want to demonstrate what is possible if you go to the full extent with this pattern. So there's a syntactic sugar in Scala that's called for comprehension, which looks a little bit like a for iteration. So you take this collection of people, and you can take each person from there, check if it's registered, and if yes, then return his address or her address. And then get a list of addresses of registered users. So this looks like an iteration, but actually there's no iteration there, because this is just a syntactic sugar. We could do something more complex with it. For example, we could iterate through two different collections at once and yield all, well, sort of do a cross join between these collections. Yield a string consisting of the first and the second value, from the first collection or from the second. So we can create a cross join or Cartesian product if you want. So this is not just an iteration, because this gets transformed into this code. So we take people, we do the flat map. We take all positions, we do the map. And then we return this string with two values combined. So this is just a syntactic sugar that gets transformed into this, because these guys have map and flat map methods. The same can be done, for example, with futures. So you can combine two futures in Scala using this for comprehension, because futures have methods map and flat map. So this means that we first execute the first future, and then take its result and pass it to the second future and execute it. So these two functions actually execute asynchronously, but we see them as two simple steps: execute future number 1, execute future number 2, and then return the result. So here again, no asynchronous computation inside the for itself. It just transforms it to this. And this is possible because futures have these methods map and flat map. So the uniformity of this pattern allows you to write this code that is pretty simple, but it hides some inherent complexity. Okay, so today I talked a lot about many features in Java, and I was so grumpy about it. Java doesn't do this, Java doesn't do that. And you may ask me, why do I even write Java? And I write Java, actually, mostly. Well, actually I like Java because although there are really lots of these unpolished gems in the language, for me, it is very understandable language. It's a language that you can process, you can learn in a single, I don't know, you can just read a book and you can put it all inside your head. You know all the features of Java. So for me, Java is like this, like a milkshake that you can drink in one sitting and you won't get sick afterwards. But Scala for me looks something like this. So this is a really, really feature-rich language that has everything, like a lot of different things. So you probably have to extract some subsets of this language to use it right. And actually the problem is that you spend a lot of time selecting different ways of doing something. Well, the pizza, or we'll eat the hamburger, and so on. So for me, Java is a really cool language that is both very simple and understandable and sort of like a lingua franca for different programmers, because, well, whenever you're a functional programmer or you like objective-oriented programming, you can understand Java code. It's pretty simple. So I think that's pretty much all that I wanted to tell you today. I hope I didn't bore you. So if you have any questions, I would be glad to answer them. That's all.
Do you mix these languages? Do you mix them? I mean, using
languages?
Yeah.
No.
Scala and Java, for example.
Well, I had some experience with mixing them. That was not a very good experience. Okay. Because when you write Scala, you want to use idiomatic way of writing it, so you wouldn't want to drag some Java libraries because they are just not written in a functional way. You would search for some Scala libraries, so usually this ends up pretty bad when you try to mix them because they just have different paradigms. I didn't mix Kotlin and Scala though, but I also know that Kotlin was developed with a completely different view on the language than Scala, so I think that's probably also not a very good way to go to mix them.
Yeah, previously you said that Java is understandable and also very powerful. powerful, and Scala is just a wealth of features that can't be comprehended. What about Kotlin? Where is it in that range?
Yeah, Kotlin was developed with the idea that the language can be both powerful and comprehensive. So comprehensible. So in Kotlin there are no powerful features from Scala that cause some problems usually with the developers, because they are, for example, like this for comprehension. Well, it looks pretty cool, but it requires a lot from you and to actually implement it. And for example, in Scala, you have like 3 levels of understanding of Scala by Martin Odersky. Actually, he created this table. Like, if you are a beginner developer, then you should use these and these features. If you're a middle-level developer, then you can throw in also these and these features. And if you're a senior developer, then these. And a parallel stack of features for the library developers. So there's so much different features that they even had to split them and explain to people that you shouldn't probably use like implicits, for example, if you don't do this kind of thing, and if you're just an application developer, because this is for library developers. And Kotlin doesn't have these many of these features, and it's both plus for me because it's pretty comprehensive, and well, it restrains you. Maybe sometimes you write code and think, well, if only I could have implicits here, for example. So for me, Kotlin is a great new language, but right now I'm afraid a little bit to use it because it did not really gain traction and didn't settle down. So I saw, for example, some problems with this language which are not yet fixed. So I'm a bit afraid.
So you said that Kotlin has a lot of nice features, or does some things better than Java.
Yeah.
What do you expect? Do you expect it to gain popularity in the future, or let's ask it that way? If you had a new service or some new system that you had to develop and you were free to choose the programming language, would you take Java or would you take Kotlin?
Right now, currently, if I had to write a new system, that was my pet project, for example, I would definitely use Kotlin. If I write the system that will have to be developed by multiple developers in my company, I would not choose Kotlin as easily. We'll probably have a lot of conversation about it because it has to fit inside the system, the ecosystem that we are using now, for example, with some application service, with some libraries and so on. So we'd have to check if everything that we already wrote now, and we have a lot of great code here written here, that it would be useful with this new language, or we would have to just throw it away and refactor it. This would be something that I would definitely take into consideration.
I started working with Java strings a lot, with refactoring all code, and I noticed that it works really nice when you do it correctly. If not, you have no idea where the compiler errors are a mess. It doesn't help you at all. You just need to start again. How does it look in Kotlin or Scala? Like, does the compiler help you if you make a mistake, or it's also another riddle that you need to solve?
Well, if you compare to Scala, this is really there's lots of riddles in compiler error messages in Scala, so you will be spending a lot of time just to understand why it doesn't compile, for example. So it's a pretty heavy language with a lot of features, and sometimes they clash, and you see that. Well, actually, I have some questions on Stack Overflow that I asked, and I wanted people to help me understand why it doesn't compile in Scala. So this was pretty, for me, well, I was a beginner, but still, it was pretty hard for me to understand why it doesn't even compile. In Java, not so much. Usually you can understand why it doesn't compile. And with streams, there's another problem because you have to debug them, and if you have some problem in a Lambda, you have to understand why exactly it happened. But modern IDEs, for example, IntelliJ, makes a pretty good job of helping you, and you can stop and separate lambdas and so on.
How about multi-threading in CRX system? Do you have a lot of multi-threading?
Multi-threading. Well, we try not to write such low-level code, because we try to rely on the spec. So if you rely on Java EE spec, for example, it pretty much handles it all by itself. So you don't usually are discouraged from writing your own multi-threaded code. So the challenges that we solve are usually not in optimizing some multi-threaded bottleneck, but in creating a correct architecture, a good architecture of a code, creating a good domain model that could be extendable. So we usually solve these kind of problems. Not so much with multi-threading now. Okay.
Well then, thanks, Sergey.
Thanks, guys.
For mining these Java gems. I think you made a big contribution today in order to get them eventually polished. And well, I realized we forgot to organize this Java milkshake and also the Scala cocktail. Bear with us, it's just beer and other drinks plus bread, so you're welcome to stay. A couple of our guys are here too. Whatever, would be a pleasure if you stay for a while. We'll be here as long as you're here. Yeah, thanks for coming.
Thanks.
Thank you.